Section 10.5 is on page 488. Talks about separation of variables. That's something that we did before, we're going to do again. And heat conduction in a rod. Consider a straight bar of uniform cross-section and homogeneous material in which temperature spread evenly or uniformly. Let the x-axis be chosen to lie along the axis of the bar, and assume this is insulated. So x equals 0, we're going to set it to be at the very beginning of this rod, and x equal L will be at the end. And u of xt is going to vary depending where you are on the rod as far as distance and how much time has passed. Assume that the cross-sectional dimensions are so small that temperature measure u can be considered constant on any given cross-section. So it doesn't heat more in one area than another. Actually, it's uniform all throughout. The second thing that I boxed, the variation of temperature in a bar is derived in Appendix A on page 522 in our book. The equation is called the heat conduction equation and looks like this, where x is between 0 and L, T is always positive, and this alpha squared is kappa over rho s, where kappa is the thermal conductivity, rho is the density of the material, and s is the specific heat of the material. Different material have different tolerance for heat. Now, I'm going to make a few assumptions. Assume that u of x0 is a function of x if time is 0 initially. Assume that t sub 1 starts at x equals 0, and suppose t sub 2 is at the very end, x equal L again, right there at the beginning, right there at the end. I'm cluttering this, let me take this off. So we assume here that the temperature in the beginning and the temperature at the end will always be 0, which means u at 0 T is 0, and u at L of T is also 0, and x is going to vary between 0 and L. This would be the initial temperature. I can do better than that. And these are the assumptions. We know that T is always positive, right? And what I'm really looking at now is if this is T and this is X, we're running between 0 and some L. So we're looking over this region. This is x equal L, and u sub L T would be at the end, and u sub 0 T would be at the very beginning. Alright, and we're looking over this region and trying to figure out what happened between those. Now comes a few more assumptions. Assume that u of xt is a function of x that depends on where you are, and a time that depends how much time have lapsed. And if I take the equation that's going to solve every problem for me, there it is. This is a partial differential equation. And why is that? Because you're taking partial derivatives. Now, Note, if this is my function, if I take u sub x, that's going to be x prime t. And if I take u sub xx, that's going to be x double prime t. And if I take u sub t, the partial with respect to t of this, that's going to be xt prime. And that's something I'm going to do on almost all of these problems. So if I really look at this equation really becomes alpha squared u sub xx is actually x double prime t, and that's going to equal u sub t, which is xt prime. Now, if I do separation of variables, I'll get x double prime over x equals t prime over alpha squared t. We're going to set this equal to negative lambda every time, no exceptions. And it has to be negative. That's what we're going to set those equal to every time. And what's going to happen here, we're going to get the first equation, x double prime over x equal negative lambda, or we're going to get x double prime plus lambda x equals 0. Also, we're going to get t prime over alpha squared t equal negative lambda, or we're going to get t prime plus lambda alpha squared t equal to 0. This is a system of equations, and those are ordinary differential equations. By making the following substitutions, we're going to convert the partial differential equation to a ordinary differential equations. Now, if I look at this piece, that should look familiar to you. X double prime, so this is recall that we did this back in the days, plus lambda x equals 0. We worked that out already. This is equation 31 in section 10.1. When we solved this, we got lambda sub n to be pi squared n squared over L squared. You could look at the notes and see that we did that. This was the eigen value or function, and the eigenvalue and the eigenvector, and they called it eigenfunction. Eigenfunction was the sine of n pi over Lx. So that was in our notes. Now, keep in mind, with everything said, if I take u of 0t, and remember, there's u. Isn't that going to be x of 0 times t of t? If t of t equals 0, then that's a trivial case. Right? And if I take the second equation, this equation, and if I take t prime plus lambda alpha squared t and set it equal to 0, what would happen? I'm looking at a separable equation. I'm looking at t prime equal negative lambda alpha squared t, or t prime over t equals negative lambda alpha squared. And if I look for t, that's going to be natural log of t equaling negative lambda alpha squared t, and I could say t is actually e to the negative lambda alpha squared t. E to the negative, and if I take what lambda equals, times alpha squared t, that would be half of the problem. Again, remember, the goal is to find this x and to find this t. There's t. And I could say now, u sub n of xt is going to equal x and t. Well, I know that t is e to the negative pi squared n squared over L squared alpha squared t, and I know what x is. That is the sine of n pi over Lx. So this is u sub n of xt, and since I'm squaring all of these variables, all of these are positive, t is positive, you know this is exponential decay, right? You know, on the long run, if you let this system run for a very long time as t approaches infinity, this exponential will dominate over the sign, and that's going to be a 0. And u sub n that we just found are sometimes called fundamental solutions of the heat conduction problem. A massive deal. Now, we assume u of xt equal the series n equal 1 to infinity c sub n times u sub n of xt, which is the series n equal 1 to infinity c sub n, and this we already found. I'm just going to copy that right there. E to the negative pi squared n squared alpha squared over L squared t times the sine of n pi over Lx. This converges. And keep in mind, if I take u sub 0 t, that's the series n equal 1 to infinity. If I let x equal 0, c sub n x0. If I let t equal 0, this piece will disappear, and I'll be left with the sine of n pi over Lx. So this is initially, I call this f of x, and guess what? Where c sub n is, and are you ready for that? 2 over L, the integral from 0 to L of f of x times the sine of n pi over Lx dx. Fourier. That's how you find the coefficient. And if you recall from 5b, finding the coefficient was tons of work, right? Taylor, all of these different things that we did back in the days. So now, let me work out a problem. I'm looking at page 495, and this is an equation. It says here, in each problem 1 through 6, determine whether the method of separation of variables can be used to replace the given partial differential equation. This is a partial differential equation into an ordinary differential equation. If so, find the equations. If you could separate it, you could do it. So remember how this works. We're going to let u of xt equal a function of x times a function of t, right? And if you recall how this works, this says t, u sub xx is actually x double prime t plus little x u sub t. If you take the derivative of this with respect to t partial, that's capital X times t, and that equal a 0. So can we separate those? Well, let's see. T x double prime capital T equals little x capital X t equal. So I could say x double prime over little x capital X equals, you messed up on t prime, right? And that should be negative. I moved it to the other side. So that would be negative t prime over little t capital T. I'm going to set this equal to negative lambda every single time. And out of this, guess what I'm going to get? A system of equations. X double prime over x capital X equal negative lambda, and negative t prime over tt equal negative lambda, or I could say x double prime plus lambda x capital X equals 0, and I can get t prime, those negatives cancel out, minus lambda t capital T equals 0. This is an ordinary differential equation, so I was able to separate it. What I did, I took a partial differential equation, which is very challenging to work out, and I converted that into an ordinary differential equation system of equations. And what do you know about systems of equations? We could write those using matrices and solve them. I'm going to stop this video here and continue the next.